Thank you very much for the introduction and for the opportunity to talk at the summit. It's been a really interesting series already, and I guess one of the benefits of talking this late in the session is that much of what I would have used in the introduction is already being well described previously in some of the talks, so I can reference back to some of those. What I'm going to talk to you today about is the hyperdiff technology, and this presentation has been put together in collaboration with one of my colleagues, Dr. Marco Longana. If I just engage with the laser pointer here, this is Marco. And fortunately, I can also refer back to Soraya's excellent talk yesterday about discontinuous composites. So on the right-hand side of the screen here, you'll see conventional composites that have formed a lot of the discussion thus far. So a matrix covered covering a series of continuous long fiber reinforcement. We're talking about discontinuous composites, in this case, short discontinuous fibers, short filaments. The difference here is that the technology that I'm going to describe with hyperdiff is in the high levels of alignment that can be achieved in these composite materials. And so what we produce are what we call aligned discontinuous fiber reinforced composites. So I'm going to talk about a brief history of hyperdiff, talk to you about how it works, and say a little bit about what sort of properties we can improve and how we can enhance the sustainability of the composites we manufacture using the technology. And I'm going to leave you then with a view of the future and where we are with the hyperdiff in its current form. So a brief history. I'm glad that the session is being chaired today by Professor Michael Wisnam. Michael led the highly successful PSRC program grant Hyperduct, High Performance Ductile Composite Technology, from which this hyperdiff technology emerged. It was one of the work packages that was seeking to try and improve one of those problems that composites typically suffer in tension. In the failure, when failure happens, is generally quite sudden and usually quite sort of unheralded. And so the whole idea around hyperduct was to try and make advanced composites that could fail more gracefully, as was said by a colleague. So the technology was co-invented by Dr. Hannah Yu, and Hannah you can see on the image on the right-hand side here. Hannah's now at the University of Bath, and Professor Kevin Potter. The technology was patented by the University of Bristol, and the first generation, the desktop prototype, which we've subsequently christened Baby Diff, you can see between Marco and Hannah here. Baby Diff is still used. It's still a very useful bit of kit, which is taken around to different shows and conferences as a means of demonstrating the technology. But most of what I should talk about today will relate to the second generation of the machine. This is HyperDiff 2G, and there have been multiple publications that have arisen from using this particular bit of apparatus. But as you'll see, it's very much a lab scale demonstrator. And in 2017, I led an EPSRC proposal that was successful in obtaining £1 million to scale this up. And so where we're going is moving from lab to a demonstrator that is more relatable to manufacture. So what are the benefits of using hyperdiff? Now the outcome of hyperdiff, the product if you like, is as you can see in this image here. Hyperdiff means high performance discontinuous fiber, and indeed the logo, Marco would want me to indicate that the logo, these particular elements that you see ringed here, relate to some of the attributes that you can see, in the sense that the edge can be feathered, can be tapered to reduce stress concentration in ply drops. The discontinuous nature of the product means that the ability to essentially follow an arc and reduce buckling and warping is particularly important. And also avoiding fiber bridging in 3D forming is something we're increasingly examining. So it's a tape, it's an aligned discontinuous fiber tape, which means it's ideal for, as a feedstock, for using in automated fiber placement, automated tape laying, and latterly fused filament fabrication, sort of thing that you would do in a 3D printing apparatus. So this is the lab scale machine. Now, this is easier to show you the way in which this operates and to talk a little bit about how the technology works, but please note that this is the second generation machine, which is, as you see, very much lab scale. It's a bit of a Heath Robinson affair of a machine that's been put together and designed accretively. But as you can see, essentially this is a waterborne process. We're very fortunate in working with Fraser with ELG, and we use materials from recycled carbon products from ELG. These are dispersed in these water reservoirs and then pumped through this myriad pipework to get to the real sort of magic happens here. This is the distribution head in which the fibers in suspension are actually projected, they're jetted through these apertures. And if we look sort of downwards on this, between the plates, what we have here are a series of plates which are finely divided. So the discontinuous fibers are projected and they strike the back plate. And as the fibers strike the back plate, they then essentially transfer the momentum, they fall, they're sucked to the bottom of the bottom of the plate by a vacuum. And so what happens is we then end up with a series of fibers, discontinuous fibers, aligned and consolidated into an aligned discontinuous fiber preform. So at this point, we've got essentially a dry tape, highly aligned, short discontinuous fibers. That's then dried, combined with a matrix, and at the end of this, we produce a tape, a pre-preg tape. Now, where Hyperdiff fits in to this process, and where we are able to talk specifically in terms of sustainability, is the way that we can operate with both new fibers and reclaimed fibers. And the reclaimed fibers may be carbon, maybe glass, maybe synthetic fibers, materials like PBI or PET, and also natural fibers. They're combined, having been aligned with both thermosets or thermoplastics via a matrix impregnation. And the composites, having been produced and used, can then be essentially disaggregated. We can reclaim the constituents, much as was described by both Soraya and Steve Pickering yesterday. And they can then be introduced into yet another loop so that the materials can then be further cycled. So I'm told that the volume's dropping off a little bit here, so I'm just going to try and boost this a bit. So I'm in a quiet part of the countryside, so hopefully you'll be able to hear this. Okay, so the challenge is that what we see at the beginning of the process is this mass of essentially like a cotton wool process. So this is a typical material that would come in from ELG, and we need to then disperse this into a waterborne reservoir. Okay, so this is the product. This is the ADF-RC. And in this particular case, this represents a thermoset, an epoxy thermoset with short fibers. In this case, these fibers are 3 millimeters in length. As you can see, the stress-strain curve gives us some impressive mechanical properties, as you can see from the ultimate tensile stress and the strains recorded. This is a high fiber volume fraction, around 55% by weight and by volume, and the modulus that we can achieve here is around 115 gigapascals with a tensile strength of around 1500 megapascals. Now you can see from the micrographs on the right hand side here the level of alignment, which is high. Now why do we perform this? If I compare the data of our tape, in this case containing purely high-strength carbon fibers with an epoxy matrix, this is very much sort of human AFP, if you like. It's a hand layup, but you can see it's quite laborious in this sense, producing it from these very narrow tapes. But in this case, as you can see, a quasi-isotropic layup, which produces, in this case, fiber volume fraction is a little lower at 25%, but the data here are the random mat, and the data for the ADFRC from hyperdiff is shown in blue. And as you can see, from terms of the stiffness, the failure strain, and the strength, the hyperdiff material is greatly superior to the random mat in all cases. So the alignment is really key. It's been described earlier. Now, as I said, this material, the drive between producing this material was to try and address the problem of a poor response in tension, or at least a rapid failure sharp failure in tension, and the need to try and produce a pseudo-ductile metallic-like response in failure. And as you can see here, in these two cases, the black line on the left-hand side, these are unidirectional laminates. In black, this is essentially a high-strength carbon, and in this case, the black is a glass composite coupon. And what we're seeing here is, as one starts to increase a second component, and here it's a blend of high modulus and high strength carbon, and high modulus carbon and e-glass, you can see that there's a distinct knee, a plateau that's reached in the properties before the material again begins to rise prior to final failure. So this pseudo-ductile response is also retained when you start to produce the quasi-isotropic material. So in this case, we've selected one example of each. Here's the unidirectional response for the carbon and the glass in red. And here the corresponding responses for the quasi-isotropic layout. And as you can see, in both cases, you get the yield strain is the same for both the unidirectional and the quasi-isotropic. The knee point is somewhat less evident in the quasi-isotropic, but nevertheless, as you can see, there's a clear plateau before the material undergoes failure. So the concept of a material that fails somewhat more gracefully is shown to be achievable. So this is about sustainability, and as was very clearly made evident yesterday in Soraya's talk, was the need to combine alignment and volume and high volume fraction of reinforcement to achieve good performance. Now, these data show for a carbon glass hybrid the highest recorded stiffness for a recycled composite. You can see the sort of values we're looking at for recyclate here, about 70 gigapascals. And importantly, as the amount of recycled fibers are increased in the blend, there's no discernible change in the properties. So in this case, the stiffness is not affected by increasing the recycled fiber content. There is a diminution in the strength and failure strain, as you can see, as the recycled fiber content increases. But this again underlines the need for introducing recyclate in which the fiber properties have not been degraded during recovery. So, as was described in Fraser's talk earlier in the session, the need to recycle multiple times is really key here, and Steve Pickering talked about this in his presentation yesterday. Looking at trying to remove materials from a thermoset matrix is very challenging, but as you can see here, the modulus and stress strain data for a thermoset material in which the virgin carbon fibers give the initial data here. You can see about 65 gigapascals. The first recycling step in which the fibers have been removed from the matrix replaced into another matrix and remanufactured, gives us a second life, and the potential for another recovery and recycling is also evident. So this is a very, very versatile technique. As I've said previously, there's an opportunity here to improve the ability for the combination of different fiber types. And in this case, we're looking at the potential to combine carbon fibers of different lengths. So in this case, a combination of a 3mm and a 6mm fiber, again, shows that stiffness is largely unaffected as you move from 100% of the 3mm fiber through to 100% 6mm. So this is a very tolerant technique when it comes to combination of different fibers. Now, in the first presentation, Tony Ryan gave a very erudite discussion about circular economy, and I would echo what was being said there in terms of the ability to use, or the necessity to use LCA to ensure that the materials can be determined in each process, to ensure that what we're actually striving to do, if we go from a linear to a circular economy, is justified. And indeed, we've applied LCA to hyperdiff to ensure that we're proceeding in the right sort of along the right sort of path. So this is the combination of bringing new fibers into hyperdiff, combining with thermoplastic matrix, looking at end of life, recovering constituents, taking out the reclaimed fibers, bringing them back into combination with a recycled thermoplastic matrix. And we've shown that for both carbon fiber and polypropylene, and carbon fiber and nylon 6, that it's possible to retain the properties and indeed even improve the properties over several recycling loops. And as you can see, the stress against strain behavior for the virgin carbon fiber polypropylene, the recycled carbon fiber polypropylene, and a second recycled step demonstrates that we're still able to maintain properties, and indeed on the second recycling, we actually get improvements in the strength, which we believe is due to residues of matrix on the fibers, as shown by microscopy, which tend to then act as a matrix-specific sizing. And we've achieved the highest properties in a carbon fiber polypropylene composite, fiber volume fraction of 26%, to get a modulus of 43 gigapascals and a tensile strength of 285 megapascals. So finally, the ability to look at producing materials with different functionality is shown here in a combination of carbon fiber and flax. This is recycled carbon fiber and flax fibers, natural fibers. And as you can see, the benefits here are one of reducing cost, improving damping, and so mitigating noise, vibration, and harshness. There is a payoff in stiffness and strength, but nevertheless, moving from a primary into a secondary use may be attractive, particularly in automotive use. So the final slide is really to look at where we are with the future. Now, as I said, the £1 million grant to develop the EPSRC proposal was to yield this third generation machine, which, as you can see, is far more, it's fully automated, it's stacked with sensors, it's a high throughput. We move from grams per day to ultimately kilogram per hour quantities. And this is supported by a large consortium, among whom are ELG already. And this, we're delighted to have been preceded by Tim Young here, because Tim's been very supportive of development of hyperdiff 3G. It's located at the NCC. And of course, it's easy to very fortunate to be able to take credit for presenting the work, but of course the work is done by a very, very large team. The hyperdiff team, both past in blue and present, is a large one, both in terms of academics, researchers, and PhD researchers. And we're very fortunate to have that team working stoically through COVID-19 and continuing to build the hyperdiff 3G at NCC. So thank you very much for your time, and hope you were able to hear that.
Thank you very much, Ian.
Thank you, Michael.
How much is the additional cost, approximate percentage, of aligning the fibres after recycling them?
That's a really good question. If you're talking in terms of economic cost, we haven't done that calculation yet. I mean, we're just completing the third generation of the machine at the moment. We've done an LCA based on obviously the energy usage and the use of three different continents. So we can say something about how it improves matters as you start to sort of shorten the lines between waste and different mixed methods of energy usage. The cost is a different question, because at the moment this is still a research instrument that we're performing. We're just stretching to manufacturing now, so we'll know very soon what that means in terms of energy usage, in real terms.
If carbon fibre is hybridised with natural fibres, can the resultant composite be recycled?
Yes, I think it would still be possible to recycle. The question would be, obviously, whether it's economic, whether it's feasible to do so, and that would need an LCA to ensure whether it is actually a workable route. But from a chemical perspective, certainly you've got two very dissimilar fibres with very different polarities, very different sort of chemical structure. So the ability to separate materials with quite different densities and polarities is certainly feasible. We've shown this very well for other compositions of glass and carbon. Just getting to the stage where we're looking at sort of second life for natural fibres. So we're not looking at that at the present time, but certainly I think it will be something which we'll need to explore further.
Okay, thank you. So perhaps a related question here is property retention of carbon fibres after pyrolysis is widely reported. However, this is often from controlled feedstock of single fibre type. Waste feedstocks are difficult to identify and segregate, especially projected to future volumes. So there's a question about whether future recycled, reclaimed fibre output from pyrolysis, which will be a mixture of fibre types, and then will the bulk properties reflect that mixture, or should segregation of feedstock be an important focus?
That's an excellent perceptive question. So I think as was mentioned yesterday by both Soraya and Stephen, and emphasised by Fraser earlier, the manner by which the fibres are being recovered is going to be really key. Now, pyrolysis is not the only show in town, as Steve said yesterday. There are other methods, and indeed at NCC we're working with them to explore decom as a means of sort of steam hydrolysis to remove matrices from fibres in order to recover the fibres with a slightly more gentle sort of method. So I think there's almost a need to examine the method by which the fibres were recovered and almost segregate those in terms of ultimate strength or the properties you might expect if they've been pyrolyzed or if another method's been used. So I think that it is important, because that quality assurance, which comes from knowing the thermal history and the chemical history of the materials, is going to be important. But I think that will be very important about determining which route is being used. And I think Fraser will probably have more to say about that in the Q&A later.
We can perhaps pick that up again in a second. In fact, can I encourage our other panelists, other speakers to turn their videos on now? And while they're doing that, just another question, Ian. Are mixed fibre length composites a way of achieving higher fibre volume without alignment? And could this provide a viable use of downcycled, damaged, recycled carbon fibre?
I think that's certainly going to be important. And as you've seen from the data on hyperdiff, whilst we're looking at a relatively narrow range, less than 1 millimetre up to about 10 millimetres, there is a range there. I'm not truly talking about long fibres. But as you've seen, the relative insensitivity of some of those, particularly stiffness, offers the chance to certainly look at those hybrids without necessarily having to go through the need for very, very carefully controlled length of fibre.
Okay. So a question for you, Tia, if you've got your microphone unmuted. At the end of life of the plane, are the composites recovered for recycling? And if not, what will happen to the materials?
So there is a group, AFRA, Airplane Recycling Association. I probably butchered that, apologies, but they do look at things such as end of life. And when we do have an end of life airplane, a lot of the content is recyclable. One of the probably challenges is in the sorting of the different materials. And then those types of composites that are used for the interiors that might have additives that are added to the resin for smoke and flame and toxicity issues. Some of those are very difficult to separate out and recycle.
What's the requirement for reclaimed glass fibers for creating hybrid fiber tape? So I'm opening this now to the whole panel, so whoever would like to comment on that, Fraser perhaps, or Ian.
Okay, so we're just about to submit a proposal at this stage. And it's always dangerous to say we're proposing something, but we're certainly looking to explore the use of recycled wind turbine blades at this present time, both principally glass, in order to repurpose the glass and impart different functionality. So if you think about the glass as being purely fairly passive, just simple glass fibers, then I agree the economics are certainly not stacked in its favor, and both Tim and Fraser have already had something to say about that. However, if you're able to chemically modify the glass and give it additional functionality, then you certainly increase not only the functionality of the resulting composite, but you also increase the value of the materials coming through. And I think if you're going to use glass for anything other than the mechanical properties we've talked about, by modifying the stress strain behavior, then I think you have to go towards having some additional functionality to make it worthwhile.
Okay. So I've got an interesting question here from Mike Hinton, if I can find it again. Disappeared. Okay. So if I was to give this topic a bag of gold to spend, what would you spend it on? What would accelerate the journey to market?
Yeah, exactly. Directed to Hyperdiff or to the other gentleman?
Well, maybe you can start and we'll open it up to the others.
I think from a Hyperdiff perspective, we are at the stage where we're already eyeing up the next generation of machine, which what we've produced is a very high spec research grade machine, which has the potential to be very close to manufacturing, but it's not a manufacturing machine. If you were to give me a bag of gold, the next stage from Hyperdiff perspective would be to produce the manufacturing machine, which would then feed into a variety of different business plans to see whether it's commercially viable.
Anybody else like to spend the bag of gold?
I'll have a go. So Mike, you're a bit late with a bag of gold. Because we just signed off on a 5-year investment plan around capacity. So one big thing is capacity, because a lot of the applications for these materials are quite high volume, and there's always that concern about supply chain security in the minds of the end users. This is moving. This is no longer being looked at in very niche applications. This is going into long production programs which have been planned for a long time, and so they've got to have absolute supply chain security. So number one is capacity, but that's really, that box is ticked. The other big thing is, I think, it's not so much into the materials research side, it's into demonstrating the applications, because there's a lot of uncertainty about what you can really do with recycled materials and how they perform. A lot of the comparisons make in comparison with virgin materials, and that's not strictly the right comparison. The comparison needs to be with what is required for a material in a particular function. And that magnesium casting example I gave showed earlier, that is an area where a very, very short carbon fiber composite, I think in the final part, the fibers are about 0.5 millimeter long. That's producing higher strength and the same stiffness as a magnesium casting. And so, making people aware of what is possible and taking away some of the fear factor around using a recycled material, that's where I think the pot of gold needs to go, letting people do demonstrator projects and really understanding what is possible.
Can I add to what
Tim?
Fraser said?
Yeah.
I think what Fraser said is absolutely spot on. I think I'd add that something that make a huge monumental difference is getting education out there to support the capacity in how to design for sustainability. How do you design an end of life? And in particular, how do you work with some of the emergent material systems so that we can capitalize and support the output and that application? Alongside that, we really need databases and a mechanism to really enable intelligent decision making, so that you can get confidence that the products are going to last. So when we have applications, they're treated seriously, and actually they're very competitive because people have the right data.
Thank you. Another question related to natural fiber composites. They've been developed and applied in some fields of industry, like in automotive. Is it possible natural fiber composites to be applied in aerospace? For example, carbon fiber composites? If possible, which part of the airplane can be applied by natural fiber composites? I don't know whether Tia wants to take that one, or anybody else would like to comment. Natural fiber composites for aerospace applications.
So whilst Tia's unlucky, so one of the things we've been investigating is demonstrating the possible applications of natural fiber composites, and also bio-derived and natural resins for things like aerospace interiors. We're seeing a lot of appetite for, if we're not going to make new aircraft, recommissioning existing ones and changing, strip out the interiors and so forth. So there's a lot of opportunity there at the moment. I don't think it's been fully exploited yet, but it's an area that's of particular interest to us at the moment.
Yeah, have you got anything to add to that?
I don't know. I think I'm at too low a TRL. Fraser?
No, I mean, I was going to say the seat back example I gave you, I know that they've looked at incorporating natural fibers into those type of parts as well, so interior type parts.
So, are you there, Tia? I've got another question for you if you are. I'm wondering whether we've lost Tia. Okay.
Tia's muted.
This is Tia. I am sorry. Please go ahead.
Okay. Yes. So, right, it's disappeared. Just let me find it again. As a UK formulator, so this is from Dominic Hopwood of Bitres. As a UK formulator and manufacturer of modified epoxy,
can you hang on for just one?
Flame retardant aircraft interiors, how quickly do you think the global aerospace community will start to accept alternatives
just a second here.
As viable alternatives?
Can you, I'm sorry, Michael, it was kind of breaking up on my end. Could you repeat the question one more time?
Yes. So this is from Bitres, a UK formulator and manufacturer of modified epoxy and phenolic resins for flame retardant aircraft interiors. How quickly do you think the global aerospace community will start to accept bio-based alternatives, such as polyfluoroalkyl alcohol resins as a viable alternative?
I think that once we demonstrate that the bio alternative can meet the requirements of interiors and others, I think that we would be eager to embrace that. You know, inserting technology into production airplanes is probably challenging, but inserting it into new airplanes would not be as challenging. And I think aerospace would be pretty motivated to look at some of those. Again, the challenge is making sure that they meet not just the technical requirements, but also back to Fraser's comment about supply chain, that, you know, there's a viable supply chain that can produce the material at the amounts and at the rates that airplane production would require.
Okay, well, thank you very much. Perhaps one final question, which I'll open up for anybody who wants to pitch in. The specific question is about the level of investment in sustainability compared to other aspects of the composite industry. So what is the level of investment? And perhaps we can also open that up to say, well, what it should be and where should the investment go? We'd like to take that one on.
What do we want for you, Tim?
I'm just trying to sort of formulate an answer. The level of investment in sustainability is very, very high. I think it's part of our job to make sure that what we're doing aligns with our output, and you'll find that the amount of funding opportunities increases. The good example is the Rediscover program we did. You'll hear more about that tomorrow with what Lucy's talking about, but that is a monumental package of work if we were to do everything, the number of participants, the amount of stuff, and it's still a drop in the ocean, but it would have seismic proportions. That is a large funding requirement. And so whatever you look at and whatever scale, we do need to try and lobby for more funding in this area, both at the academic level to support industry to actually recover and start developing new products in the right way, because otherwise they'll come out of COVID and the current economic scenario, and we won't necessarily have supported them to do things. And then also in the RTO scape, how do we pull through all of those things? So it isn't big enough is the answer. We'll do with what we can with what there is.
Anybody else like to comment on that one?
I mean, we can give you a number on it, but what we can say is that from an OEM perspective, or what we see from the OEMs, there's a lot of interest around sustainability. And so they're putting effort into this. What that means in terms of money, I've got no idea. I think where the gap is, it's connecting the OEM desires and a nascent recycling industry. It's making the whole supply chain come together. So the intermediate products, the tier ones to design and manufacture. So it's getting a connected supply chain that's able to meet the demands of the OEMs, I think, is what's important.
I think I'd like to attack it from a slightly different angle, in the sense that realistically, this is something we have to embed throughout the supply chain, from raw materials manufacturers, intermediate producers, and OEMs. And so I would, if rather than Mike's pot of gold, if I were given some sort of opportunity to kind of influence what's going on, it would be in terms of legislation to ensure that what we're actually encouraging is whether it's LCA from top to bottom, or whether it's a more responsible means of sourcing the chemicals and the feedstocks in the first instance, and how we go about sort of introducing it throughout the supply chain as part of the production process, to ensure that we're not just greenwashing, but making it very clear that we're actually doing this from a responsible perspective. So we're quantifying what sort of benefits we're seeking to impart, and whether those are actually justified. Going right back to what Tony was saying in the first presentation, we can't simply assume that because we're making an intervention it's the right one. We have to ensure that each is done on a case-by-case basis, and that really has to be the way going forward. Speaking as a chemist who has made many materials and formulations in the past, one has to ensure that LCA is embedded at the very, very heart of this.
Well, thank you very much. And well, thanks to all our speakers. So we had a really excellent session. So really appreciate your contributions. And thank you also to our audience for joining us and participating. And we hope to see many of you tomorrow at our Sustainable Composites Products session, and then on Friday at the workshop. Thank you very much.